Hello, my name is Quentin Odenthal, and this is my video submission for my part of Group Project 3 for CSCE A311. And I'm going over part 1 of the assignment, and the first part of part 1 is inserting 8 into this. I wanted to copy that. Let's copy that. Inserting 8 into this heap. I'm going to zoom in. Alright, so we've got our established heap right here, if you ignore the 8 for a second, and we need to insert 8. And we're going to put it right in the next available spot, which is right there. We go to drawing, switch to black. Boop. Ooh, that's a huge line. That's alright. But this is no longer a valid heap, because we got a parent of 5 and then a child of 8, and the child's never supposed to be greater than the parent. That's how a heap works. So we need to do some swapping around. Go to select. So first we're going to swap the bigger child with the parent. So we take 5, put it down here, take 8, put it up there. Boom. And now we check again. 8 is still greater than its parent, 7. So we're going to do it again. Take 8, boop. Take 7, boop. Boom. Now we check again. 14 is greater than 8, and 8 is greater than both of its children, so we're good. It's now a valid heap again, and that's how you insert 8 into that heap. Zoom back out. So that's part 1. We don't need that anymore. Part 2 is a little bit different. Same starting heap. Let's take this. Actually, I could just paste, huh? Boop. Alright. Zoom again. Scroll. Alright, we don't need 8 this time. So we start with our established heap again. But this time, we're going to pop off the max. Where we return it to the screen and then we just delete it from the heap. So it's gone now. Bye-bye. And what we do next is we actually take the last element in the whole thing, boop, put it at the top, and then we're going to heapify all the way down. So, to do that, we check both the children of 1, which is 7, right? Let me go to drawing. Which is 7, right there, and 10 right there. And 10's bigger, the biggest of the two, and it's bigger than 1. So we take 10, we swap it with 1. Oh, just chopped it in half, didn't I? Let's try that again. There we go. 10's now the top. And then we do the same thing again with where 1's at now. So it's smaller than both of its children. So we take the largest child, which is 9. We're going to whoop, and then take 1, put it down there where 9 was. Oops. And then we're going to put 9 right there. And now we check again. 1 doesn't have any children. And as you can see, it's a valid heap again. 10's the greatest thing around. It's bigger than both of its children. The children of the children are smaller, and all the way down it's a heap again. So that's how you remove the max. Let's take this whole shebang and just into the ether. And now, I'm going to take this. The final part of this problem is we need to go over pseudocode for determining if this is a max heap. And a max heap has a few things about it. So, first thing, it's a valid heap. It needs to be a valid heap. Oh my god, that is way too big. Needs to be a valid. Okay, typing at this size is not great. I'm gonna zoom out. Let's take this, bye-bye. Alright, it needs to be a valid heap. Wow. So the parent needs to be greater than the children all the way down, whatever valid heap stuff. And what makes a max heap special is that this bottom layer, the bottommost layer, needs to be totally filled. So each node either needs to have 2 children or no children and be a leaf. So that needs to be filled. Oop, shoot. Go back. Another thing is, I guess this kind of goes with the filled thing, but you can't have a node, let's say 9 with a child of 8, and then no child over here. It has to have 2 or 0. So that can't happen. Yeah. So now let's go over pseudocode to figure out if it is indeed a valid heap. Max heap, rather. A valid max heap. So step 1. This is a recursive algorithm also. So let's start at the root, the head, whatever you want to call it. We need to check if the current node is a leaf, which means it doesn't have any children, which it does, so it's not. Next, we need to check if it only has one child, because if it only had one child, then it wouldn't be a valid max heap anymore. But it has 2 children, so that's good. We need to check if either child has a greater value than the parent, which would make it not a valid heap in general, but 14 is greater than 10 and 7, so we're good. We need to and then we need to recursively call this function for the left and for the right. So then let's focus on the left one. We go through our list again. I could write it this time. So, is it a leaf? No, 7's not. So, and then we check one child. Boop. It doesn't, has 2. And then we check leaf, one child. And then we check, is it less than either of its children? Less than child, which 7's greater than 6 and 5, so we're good. Oh, that's an X still. I'm dummy. And then we recursively call it for its left child, 6, and the right child, 5. And let's do 6. Is it a leaf? It is this time for 6. I guess I could do it in red, that's a little bit more clear. So we don't even need to check the other stuff, we just return, let's say 0, because we're going to start counting the depth. And then this one will be 1, and then this one will be 2. We use that for comparing the depths of different branches to make sure everything's all level, which proves that this is flat instead of having things like this. So, is a leaf, this one is, so we bump back out to 7. The other part of 7, which the next part is recursively calling it on the right side. So we check 5, I'll make 5 green. Is it a leaf? It is, just like 6. So we go back to 7. And then the last part of this, since 5 returns 0, and so did 6, then we need to compare if our left number, which is 0 right now, and our right number, which is also 0, these need to be equal, because you can't have unbalanced branches in any way in a max heap, because everything is just level right there. So the left and right branch, tree, whatever, of whichever node you're on, which right now we're on 7, needs to be equal. So is 0 equal to 0? It is. We're good. And then if that's the case, then we return the depth of our current node, which is 1, which is 0 plus 1. And it kind of works for everything. And then you send that back up. So now we're back to 14. And the last thing we did on 14 was check 7. So let's go to blue. I like blue. So now we need to do the whole thing with 10. And then, so 10 is a leaf? No. One child? No. Less than child? No, because 9 too. So then we go to 9. It is a leaf. Let's go to purple. Leaf, check. So 0, 2, check. 0, it's a leaf. Send it back. So 0 equals 0. We're good. And then we return our 1. This is depth 1. Back to 14 again. So now we're comparing 14. So is 1 equal to 1, which is the depth of 14's left and right. Man, this is getting a little bit. And so we compare those. That's not what I want. Those are equal. Check. And then we return the depth of 14, which is 2. And then since 14 is the root, that'll actually be our last. We're totally done with this function now. And we return 2. And then we're going to have an interpreter function on the outside that takes whatever this recursive thing spits out. And if it's 2 or something, that means it was a valid heap, a valid max heap, and everything went well, and that's just the depth. But if it returns some value that I chose -1. If it returns -1, that means that it's not a valid max heap. So like if something had 1 child, which makes it not a valid max heap, then you'd instantly just return your -1 value to tell the whole thing like, hey, something's wrong, it broke a max heap rule, not a max heap. And then return 1 all the way up. And then it's like, and then it says not max heap. And yeah, that's how you figure out if it's a max heap. And also it returns the depth of the thing, if it is max heap, which is kind of nice. But yeah. Yeah. Okay. And that's that. So yeah.